Welcome everyone. In today's lesson, you're going to need your reference table and also a calculator. The first thing we're going to do is we're going to go to page 12 of your chemistry reference tables and look at table T. On table T, there is a new mathematical equation that we're going to be looking at and also using today, which happened to be known as the combined gas law. The combined gas law is, according to what we know on the reference table, is P1 times V1 divided by T1 equals P2 times V2 divided by T2. Just as a reminder, we know that P stands for pressure, and the appropriate units for pressure can be in atmospheres, kilopascals, torr, and also millimeters of mercury. We have V standing for our volume, and the appropriate units for volume could be milliliters or even just liters. And then finally, temperature. The only appropriate unit for temperature happens to be Kelvin. So if you're given a temperature other than Kelvin, you must convert. And since we're on the back cover of the reference table, you should remember that the conversion from Kelvin to Celsius is Kelvin equals degrees Celsius plus 273. So remember that the back page of your reference table gives you all the mathematical equations that you could possibly need. Now, before we start using the combined gas law, I do want to explain all the gas laws that we learned and how this combined gas law puts them all together. So the combined gas law actually combines Boyle's law, Charles's law, and Guy-Lussac's law. And I want to kind of prove it to you mathematically and show you that each relationship is within this formula. So let's take a look at first Boyle's law. Now, in order to understand this, the first thing we have to realize is that P1 times V1 divided by T1 equals P2 times V2 divided by T2 still equals a constant, just like we learned before, that this is constantly going to have a constant value that we're going to see over and over. Now, from there, we can say, all right, as long as we know that in the beginning and then after is all equal to a constant, we can keep certain variables constant as well. So in this case, in our first scenario, we're going to say, because we want to look at relationship between two variables, let's get rid of temperature. So we're going to keep temperature constant. When we keep temperature constant, it's almost like we can get rid of it in the equation. So we end up instead, from the combined gas law, instead we get P1 times V1 equals P2 V2 equals a constant. By removing temperature, because it is the same or it's constant, we end up with this formula. Now, from here, we can even simplify it. Instead of talking about 1 and 2, so beginning and end, we can just say, okay, PV equals a constant. And we've seen this before. Now, from here, in order to understand the relationship, we are now going to take this and we're going to split the variables. Remember, in order to get an equation, we put the variables together. But to get the relationship, we split them. So in order to split them, in order to put P on one side of the equation and V on the other side, I'm going to divide both sides by V. By dividing both sides by V, I'm allowed to remove the V on the left side, and I'm going to put it on the right side. So we end up getting P is inversely proportionate to V. Constant could be the number 1. So this is the relationship that I have. And this is an inverse relationship. It's 1 over V. And not only is it an inverse relationship, it is specifically Boyle's law. And we learn that Boyle's law has a relationship between pressure and volume. As we increase one, the other decreases. Or vice versa, as we decrease one, the other increases. So that's one. So we were able to find Boyle's law or Boyle's relationship from the combined gas law. Now let's keep going. Let's try this also for Charles's law. In Charles's law, we only relate volume and temperature. So that means that we have to keep one of the three variables constant. So in this case, we're going to keep pressure constant. By removing pressure, we end up with a formula of V1 over T1 equals V2 over T2, and that all still equals a constant. Okay, so now that I know that, I want to be able to simplify it. So it just becomes V over T equals a constant. I don't need to worry about the begin and the after. I just want to look at the relationship. Now, in order to algebraically move the variables to the other side of the equation, I have to move one of them. So I'm going to remove temperature. Since temperature is divided, then I have to go in the opposite operation. So I'm going to multiply both sides by temperature. Temperature over 1 is just temperature. By doing that, I'm allowed to cancel out temperature on the left side of the equation. And I simply get, in the end result when doing all the algebra, V is directly proportionate to T. However, we didn't learn it that way. Temperature is actually the independent variable, so instead of writing that, it's actually temperature is directly proportionate to the volume. And the reason why I switched it is because temperature is the independent, and we learned that the independent is always written first. Now, what this says is that as I increase temperature, I increase volume, or vice versa. As I decrease temperature, I decrease volume. They're directly related to one another. And this happens to be Charles's law. Finally, I want to show that I can also get Gay-Lussac's law from this. And Gay-Lussac's law is a relationship between temperature and pressure. So that means for the last one, I need to specifically keep my volume constant. By keeping my volume constant, I end up getting from there P1 T1 equals P2 T2 equals constant. I'm going to do just like I did before. I'm going to simplify. I'm just going to say, all right, P over T equals a constant. And then I want to get my variables on either side of the equation. So I mathematically need to move the variable. So I'm going to multiply both sides by T over 1. It's just algebra. And I end up getting from there really the relationship that I want, which is P is directly related to temperature. But we learned that we write the independent variable first, so it's actually just temperature is directly related or directly proportionate to pressure. This is the actual relationship. So as I increase temperature, pressure will increase. If I decrease temperature, pressure will decrease. And this was the last gas law that we learned. This is known as Gay-Lussac's law. So the combined gas law actually puts all three of the most important gas laws together. And we're able to look at the relationships. So if you don't memorize the relationships, then realize that you can easily find each of the relationships from the combined gas law. All right, now, before we start working on some mathematical word problems using the combined gas law, I do want to remind you about the 4-point rubric. Every math problem that you're going to see in chemistry and physics and in college requires a certain amount of steps that actually act as your work or that prove that you understand what's going on. So you have to remember to follow the steps in order to get all 4 points. And I'm going to be looking at this on your worksheet. So the 4-point rubric allows you to get 4 possible points. The first possible point is really to write the mathematical equation. And you should know that the majority of the mathematical equations for chemistry are on the last page of your reference table. There are some that are not there that you have to memorize, but the ones that we need the most often are there. Once you write down the mathematical equation, you get that 1 point. And from there, then you can start going to complete the question. You should be rereading the problem if necessary. You should create a chart of the givens if necessary. Now, your second point is now, after reading the problem, you're going to specifically substitute the values from the problem with the proper units. And some of you get lazy and you don't want to write down the proper units. The units are given to you in the word problem. So write them down next to the value. And you have to put it in the correct location it is in the mathematical equation. Now you're going to solve, you're going to do algebra, which you should learn how to do properly, okay? But the last 2 points are actually together. The last 2 points are really just the answer that you receive, but you have to be careful. In the proper number of sig figs, and some of you are going to have to review your sig figs rules. And not only must it be in the proper number of significant figures, but you have to have the correct unit. So if you're solving for volume, then you have to have a unit that is appropriate for volume. And that's why I told you the units in the beginning. All right, so let's take a look at a couple of sample problems. And make sure you have a calculator. Pause the video if you need to go get it. But that's the only way that you can learn, is to actually do the problems. So here's sample problem A. They give us a lot of information in the problem, and you have to read it, and sometimes it's important to underline if you must, highlight, do whatever you need to. The chart that I have on the right-hand side is optional. I'm going to draw it there for you just so you understand where the values are going, or which one is which value, and also the appropriate unit. You don't necessarily have to do that, and once you get better at this, you don't have to draw a chart. But if you're struggling, put the chart together so you can see the numbers in front of you. Okay, so a gas has a volume of 100 milliliters. All right, so I have a unit, I have a number, that's important. So we see that the volume 1, or the beginning volume, is going to be 1,000, not a 100, sorry, 1,000 milliliters. And it says the temperature at 20 Kelvin. So this now becomes my temperature 1, which happens to be in Kelvin, so I don't have to convert anything. So 20 Kelvin happens to be there. And they give us a pressure of 760 millimeters of mercury. So I'm going to write down 760 millimeters of mercury here. Okay, what will the new volume be? So there's the question. They're asking for the volume. So my volume 2, or my new volume, is going to be my unknown. When they have the temperature of 40 Kelvin, and the pressure specifically of 380 millimeters of mercury. So I just read the problem, I put the optional chart together. Now here's where I apply my 4-point rubric. The first thing I'm going to do is I'm going to write my equation every single time. P1V1 over T1 equals P2V2 over T2. The reason we write the equation is because we want to substitute with the numbers, with their units, put them in the right place. So now that I know the order is pressure times volume divided by temperature, I'm going to put the values that I have in my optional chart right into the formula. So pressure is 760, you must write the units, times the volume of 1,000 milliliters, divided by the temperature 1, which happens to be 20 K, equals, on the other side, 380 millimeters of mercury. I have to write the value and the unit. Volume 2 is my unknown, and I'm going to divide it by 40 Kelvin. So this is how you get 2 points. I got 1 point for the equation, and now I have 1 point for substituting with the correct values with their proper units in the correct places. From here on in, it's just algebra. Use your calculator, use cross multiplication, use whatever you need. That's kind of the work for yourself. Some of you like to use the calculator right away. I like to write the numbers down so I see it, just in case I make a mistake and I have to look at it again. When I simplify, I end up getting 76.0000 divided by 20. And now since this is my work in the green, I don't need my units anymore. I satisfied my 4-point rubric, and now I'm just doing this for myself. And then I'm going to write 40 there without a unit. I'm going to cross multiply. Okay, if you remember to cross multiply, you go across this multiplied by that, and that multiplied by that. All right, you get a bunch of numbers, 304, 1, 2, 3, 4, 5 equals 7600x. I have to solve for x, so I'm going to divide both sides by 7600. And I end up getting my x, which is really volume 2, to be specifically 4,000. Now, once I get to this point, I need to get my answer in the right number of significant figures with the correct units. So I'm not done yet. Some of you like to think you're done, but that's not it. So my last two points are actually important. If I go back to the original problem and I look at all the values I'm given, I have to find the least number of significant figures. This one has one significant figure, 1000 ml. This has 2 sig figs. This has 2 sig figs. This right here has got 3 sig figs, and 380 millimeters of mercury that has 2 sig figs. So my answer must be in one significant figure. Because my answer has to be in one significant figure, I could easily just write down 4,000. Be careful, do not put a decimal down. If you put a decimal down, you change the number of significant figures. This is going to be one significant figure, and then my unit has to be appropriate. If my V1 was in ml, my V2 must also be in ml. So this is my answer. That's my last 2 points. That's the correct number of significant figures, and that's the correct unit. All right, so this is using the combined gas law when all 3 values are given. But I want to show you what happens when we change it a little. And the question is simple when they start to talk about something remains constant. So sample problem B. In sample problem B, it says what volume will a 300 ml sample of gas at STP, and this is a trick. Remember that STP is actually a value without giving you a number, of a gas at STP occupy when the pressure is doubled at constant pressure. And here's another trick. At constant, not pressure, is doubled at constant temperature. Once they talk about constant temperature, I can literally get rid of it from my equation. So instead of just working with P1, V1, T1, P2, V2 over T2, since the question says constant temperature, I can remove that from my equation. So my equation gets simple. It becomes just P1, V1 equals P2, V2, which happens to be just Boyle's law, so that you can keep that in mind and think of it just to make sure that it makes sense when you get done with it. All right, so now let's plug in some numbers. It says what volume with a 300 ml. So 300 ml is a volume, because I see the milliliters. So when in doubt, if you're not sure, check the units. It says at STP. So my pressure has to be standard pressure. I can use any value that I want to. I can use 1 atm, 101.3 kilopascals, 760 millimeters of mercury, 760 torr. It's probably easier mathematically to use the value that has the number 1. So I'm going to write down 1 atm. Now the question says when pressure is doubled. So since pressure is doubled, then I'm just going to double the pressure the second time and make it 2 atm. And my unknown happens to be V2. Right? So I made this problem easier by getting rid of temperature. Even though they said that standard temperature is there, I don't have to worry about it because it's at constant temperature. So now I have 1 point for writing down the equation, and I can simplify the equation as much as I want to, and I did. I'm going to write down 1 atm. Now I'm going to plug in with the values and their units. 300 ml equals 2 atm, and then multiplied by x. So I've gotten my second point, right? Now I'm just going to do the work. I'm going to simplify. I'm going to put the numbers in. I'm going to isolate x. All right, that's just algebra. And I end up getting a value specifically for x, which is really v2, of 150 something. But before we write down the units and before we do anything, let's evaluate for sig figs. In this problem, they only give me one number. So I go back to that in the problem. I don't go back to the ones that I had to find, like STP I had to find on table A. That's something I had to find. I only go back to the values given in the problem. So this number, 300.0 ml, actually has 4 sig figs. So my answer has to be in 4 sig figs. Right now it's only in 2. 150 without a decimal is in 2. So I need to convert this. To get to 4 sig figs, I need to put in a decimal, and not only just the decimal, I need to add another 0. That's 4 significant figures. Now I need to check my chart. If I'm finding V2, my V1 was in milliliters, so my units now are in milliliters. And that's my answer for sample problem B. Okay, let's go one more, just to show you another trick that might occur. So sample problem C. In sample problem C, they give us a whole bunch of values, but I want you to pay attention also to the temperature. They give you the temperature in Celsius. Because they give you the temperature in Celsius, you must convert to Kelvin, and that's important. So it says a 2.5 liter sample of gas. So I see liter, so I know that's my volume 1. 2.5 liters, I'm given. I am given 20.0 degrees Celsius. That's a temperature. But once I know that it's a temperature, 20 degrees Celsius, I want to convert it into Kelvin right away. So we already know that Kelvin equals degrees Celsius plus 273. So 20 degrees Celsius is really just 293 Kelvin. When the temperature is raised to 273 degrees Celsius, so once again another temperature in degrees Celsius, I want to convert it. I end up getting 546 Kelvin, and the pressure remains constant. So be careful. They just told me that the pressure remains constant. If the pressure remains constant, I can simplify my equation by getting rid of pressure altogether. And then they asked for the new volume, so the new volume, or V2, is your unknown. Okay, so back to the 4-point rubric. I'm going to write down the combined gas law. Some of you that don't want to do the chart, that's fine. Let's just write down the equation to get the 1 point. I know from the equation that they said that pressure remains constant, so I can eliminate that from my formula. And then now I'm just going to plug in my values. So I'm going to have my volume 1 of 2.5 liters, my temperature 1 of 293 Kelvin, equal to my volume 2, which is my unknown, and my temperature 2 is 546 Kelvin. From here I'm going to cross multiply. I'm going to take that one, multiply that side, multiply that side, and now I'm just going to do my own work. So I don't need to really put in my values, my units. 2.5 times 546, I end up getting 1365. And 293 times x gives me 293x. So I isolate x, I solve from what I need to. Whoops, didn't need to do that. In order to isolate x, I'm going to divide by 293 on both sides. And I end up getting my volume 2, when I solve for it, to be 4.658703072. All right, lots of decimal places. And this is where I need to now find 4 sig figs. If I check my problem, this is in 2 sig figs, this is in 3, this is in 3 as well. I'm only using the numbers that I'm given, not the ones I convert, not the ones I find. So my answer has to be in 2 sig figs. So remember that we now need to round properly in order to get 2 sig figs. So I'm going to count from the left, 1, 2 spaces, and the next digit right after I count, that's my helper number. That helper number is very, very large, so I have to round up. So I end up getting as an answer of 4.7, and the units for this case happen to be in liters. So my answer ends up being 4.7 liters. Okay. Now I want you to also recognize that since we simplified the formula, this is Charles' law. And we know that Charles' law is a direct relationship. So just to make sure, if you want to make sure that it's worked, I see that temperature increased, which means that my volume should also increase as well, and it did. So you can use the relationships that you know just to kind of make sure that you've done the math correctly. It's almost like a second check. If you recognize it as Charles' law, or you recognize that volume over temperature is a direct relationship, then you can make sure. And I see that. Temperature increases, volume increases. All right, did the problem correctly. Okay, now you're going to try some on your own. You have to try them to learn. You're going to make some mistake, which is perfectly fine, but I'm going to be able to post an answer key and go over some of the problems with you. All right, that's it for now. I'll see you in the next lesson.